Hey everybody, Mr. Stewart here, and I created a screencast to help support us with working our way through number 6. Now just remember what we're doing here is we are taking data and we're creating models, so graphical as well as algebraic models, so none other than equations. So these models are being designed to help us to solve particular problems. So in this one here, we're talking about music downloads. Again, you began this last week. So there were a series of questions that went along with the data table, and there are two in particular. Okay, so if you're on your in your textbook on page 325, you're going to see parts A, B, C, D, and so on and so forth. But I mean, to be honest with you, there are only two phrases that I think are most important. It doesn't mean that the other ones are not. It's just that nothing else is accessible or possible without considering these two statements. So one, which I've basically taken a snapshot of from the textbook, is which model appears most suitable, and then followed by generate a suitable model for the data. Okay, so very quickly what I'll say here, and if you hear a little bit of tapping in the background, that's because I'm writing on the screen actually with the stylus. It would be better to use kind of a tablet that's remote, but we'll just have to go with this here. So models meaning, generate a suitable graph and or generate a suitable equation, because either representation, graph, or equation could be used to solve any particular problem related to the data set. Now, the question being also important is what is meant by suitable? Okay, so what is a suitable model for any particular relationship? Okay, so in order to determine the suitability, and I'll just underline that again, really what we're after here are the various models. So for instance, can we show with any degree of certainty that it's linear, right? And with what certitude could we show that it is or is not quadratic? And lastly, is there any reason how or why we could show that it is or is not exponential? Okay, so that's what we need to do at this point in time, and then we can generate the suitable representation, be it a straight line, a parabola, or an exponential curve. So let's take a look at the data that we have in front of us. So we have our t-chart, day number will be x, and the number of downloads will be y. So we need to figure out what model is going to work for this. So you can do it two ways. One, you could go right to the tech. So we can go right into Desmos. Let me grab that for you. I've already preloaded the data in. Okay, and you notice I can't see a thing on my screen, and looking at the y values and the x values, the scaling is just totally off. So with Desmos, I can pinch and zoom in, but even doing that, that doesn't really show me a whole lot. So if you ever come up against this, where you're using these huge values, you really do need to set your scale accordingly. So even if we start by, if you press on the wrench at the top, what we'll do is we're going to set the x-axis. Start the x-axis just to the left of try that again here. Make sure it responds properly. So let's go minus 100. Okay. And then let's max it out at, you can see that there's maybe even up to 100. That might even be too large yet, but let's try that. You notice there, just by erasing that, it's spread is a lot better. And what you can see now is that it looks like we're up to, 14 obviously is the largest x value. So even if we set that at 20, let's try that. Perfect, look at that. That's excellent. Okay, could be better, but let's check the settings on this here. Okay, well, it's good enough for now. I'm not going to change things too much. So based on what it looks like this point in time, and we can adjust the scale later on, it does look like it is a bit linear, but then again, there is a bit of a curve as well to it. If you really want to generate more certainty about that, we can definitely affect the scales and work with the scale to bring those points into better view. But then again, we can settle this too by looking at the data in the table. So if we went ahead and calculated our differences, so you'll notice that the change in x all the way through, which we refer to as delta x, are all positive ones. So all the way through you'll see that. So increments of 1 day. Whereas over here, what we can do is we can start calculating a number of things, and we could start by calculating the first differences. So we should be calculating first differences, because if they are the same, right, so first differences are the same, our conclusion is linear. Then we could take this first differences. If we found the second differences, or the differences in the first differences, and if they're the same, then we know we've got a quadratic. And you see, I mentioned earlier the nonlinear nature, but if we really want to know, this is one way we could tell without having to manipulate the graph too much. Then thirdly, if we calculate ratios, or what we call common ratios, which is really about percent growth, so percent increase, or percent decrease or decay, we would have exponential. Okay, so again, you might hear some tapping in the background. That's just the stylus against the tablet screen. So with that being said, that's relatively painless. We can go ahead and take a look at those. So last week, a student had created a data table for us, and I'll take you there now. So I posted that online, and a little hard to see, maybe not. You can tell that in the first column here, 106, 112, 117, 123, these are all the increases in y, or the first increase, the first difference in y. So the second value, take that, subtract the first, get 106. Take the third value, subtract the second, get 112. Okay, so it's always subtracting one value from the subsequent value to get your first difference. The student has also gone ahead and created a second difference column. So the difference between 106 and 112 is positive 6. The difference between 112 and 117 is positive 5. So what's most notable about these is that the first differences, are not the same, and there's quite a bit of difference between them. And then if you look at the second differences, we do see that they are closer in value, but they themselves are not equal. Okay, but given they are close in nature, I would say this suggests certainly a non-linear relationship. So there's only one more thing that we do need to do. Okay, we need to calculate what we call ratios. So it would be to our benefit. Let me see if I can capture this here. Just a quick screenshot. And I'm just going to capture the number of downloads column. We'll go back to the lesson file. Just drop that in there. Try that again. Looks like it hasn't. Oh, there it is. It took a moment to get it through. So what we'll do is we'll calculate the ratios. Okay, to confirm or deny that it is exponential. So with our first ratio, what we would do is take the second value, divide by the first, so we'll find the quotient of those two numbers, see what it is. We'll do that again for the next pairing, and we'll take 2342, and we'll divide that by 2230, and we'll just continue the pattern on and on until we get to the bottom. So let's check that out right now. 2230 divided by 2124, 1.05 approximately. And then we'll try once more with the next set of values. 2342 divided by 2230, 1.05 approximately. So you can probably get the sense all the way through that that ratio is going to be about 1.05. So as far as growth is concerned, okay, that is equal to 1 plus 0.05. So the 1 accounts for the original values, so 100% of the value you're working with, and then the 0.05 is then going to account for 5% growth on top of that. Okay, so that would be 5% growth rate. So with a percentage, right, by definition, with a percentage rate of growth or decay, we're talking about an exponential relationship. Okay, so it has to be exponential. So if we go back in here, we are now deciding that this is the relationship of choice. The reason being is that there is a common ratio of 1.05. Thus, the relationship is exponential. So with that being said, recall that from our notes, there are a variety of different equations. For the exponential, it's y equals a, initial value, multiplied by b, so the base b, to the x. Okay, where b is, depending on the context, either a growth factor or a decay factor. In this case, we're talking about growth. The other models, of course, quadratic, when it comes time to using it, y equals a, trouble writing this down here, let's try that again, y equals ax squared plus b times x plus c. Okay, now the a and the b, okay, have different roles in that equation than they do the exponential. And then linear y equals mx plus b. Again, the b in that equation is different than what you would see in either quadratic or exponential. Okay, so let's deal with the exponential equation. Let's figure this thing out. So far y is going to be the number of downloads. The value of a, we don't have that at this point in time. That's the Y-intercept, or the initial value. And you can see in our table, right, that we don't have that value. See, this is the x column here. 2124 corresponds to a value of 1. 2230 to an x value of 2, and so on and so forth. So we have to come about the y-intercept a little bit differently. And y is where x is equal to 0. So we need to get that number. So when x is 0, what is y? So there's a couple ways we can do that. Just reflecting on what we've already been doing, and find the right slide, here we go. We do have the b value. Okay, remember that that was the common ratio. So the common ratio is 1.05, and that's all to the power of x. And the x value, actually I'm going to put that inside the bracket with power, with the base, because that is a power itself, and we have to do that first. And x is the number of, I believe it's weeks from the problem. So let's go about finding that y-intercept. There's a couple of ways we can do that. Okay, so we are currently generating the suitable model. So I just want to record what we have so far. So to get that y-intercept, two ways to do it. So one way would be to graph, and I do want to show you that because it's important that we are able to utilize Desmos efficiently. And with that, we'll add an equation. So go to the drop down and add an expression. And much like what was written already, so y equals a multiplied by b to the power of x. So to the power of is this key here. So a to the b to the x. And we're going to add sliders. So say add all. The b value, we've already figured that out, is 1.05. So if you didn't have all that data in front of you, you could adjust this value to get the right fit. And you'll notice that nothing's happening right now. Okay, so for a very good reason is we have not yet drawn the curve up to where the y-intercept would be. So it looks like it's going to be just above 2000. So if I put in 2000 as a value, you'll see that the curve is drawn up nicely. Okay, we could likely increase that value a little bit more. Okay, but that would require us to zoom in a little bit so we can sort of see. You can appreciate how the curve is just riding underneath those points. So if we increase that by a slight amount, so let's try 2020 and see what that does. 2020 does bring that curve right up almost through all of the points, at least through their center. So I'm kind of happy with that as a y-intercept. So let's head on back to the main problem again, and just want to reflect on the data table in the context of the question. So on day 0, right, so before tracking the downloads, there would have been a point in time where there was 2020 downloads. So that means our equation is now y equals 2020 multiplied by 1.05 to the x. Now there is another way we could have arrived at that, and that involves just reasoning numerically. So if you look at our table, over here I mentioned that if you know what x is, you can figure out your y value. So if you focus on this part of the table here, if we were to go backwards from 2124, okay, so instead of multiplying, because that's what you would do moving in this direction here, you would be continuously multiplying by 1.05. So we'll just divide by the ratio going up. So that b value, the growth factor in this case, if we take 21 2024, we divide that by 1 point, oops, sorry, that's not what I meant to say. That's your y-intercept. Let's change that here, make sure it's right. Y-intercept, and divide that by 1.05. Okay, so we should get something close to 2020, and here we have 22.8, so we'll take about 2023. Okay, so certainly our graphical y-intercept, our estimation there, very close to what we've calculated using the values in the table. Okay, so there's two ways to come up with that. So just to quickly review what it takes to be successful with these types of problems. So number one, with that data table, I would highly recommend first thing to do is to think about your ratios. It's also to think about the other models, so be it linear or quadratic, and that's where coming in and looking at those tables is important. Okay, so you can see the first and second difference columns there. So get that done and make a decision. And once you've rendered a decision about the type of model, then go and look for the equation. So is it linear? Is it quadratic? Is it exponential? Okay. Once you have those values, you can then start looking at finding slopes, y-intercepts, growth factors, all of these things. And that is actually a feature of the next question that you need to do. So once that's done, you have your equation, you'll have your graph, and last but not least, you'll be able to use the model. Okay, so with this question, we'll wrap this video up here fairly soon because we're well above the 20-minute mark. But very quickly, let me show you here. So we'll open up this file. This is just a scan of the textbook. And it doesn't seem to want to open right away. Let's try that again. Oh, there it is. It's going to want to open multiple copies now, I guess. Right, full screen on this. So scrolling up through the problem, you'll see here at the bottom, it says use the graph to predict when you'll reach 10,000 downloads, and then use the equation to predict the number of downloads after 20 days. So, it's expected that you can do both, and you may not be prompted to do that. You might just be asked to find out, and you'll have to go through, right, A through D in order to get to E, but that may not be explicitly written out. So if we use the graph to get to 10,000 daily downloads, okay, so we're just going to take a moment to go, really scroll up until we hit 10,000, and you can see it here. I'm just going to type in a horizontal line, y equals 10,000, and that's going to help me connect to this point here. So that's another little feature you can use too. If you're trying to read graphs in Desmos or on a graph period, it's like taking a ruler and running across, the line that you're looking at or the y value you're looking at, and you trace it across, and it's about 32.7. So we're going to need, 33 days to hit and exceed 10,000 downloads. Now, on the other hand, there was another part of the question, part F, asks about predicting downloads after 20 days. And you could use the graph to do that, and that's not a hard thing to do. What we would do is, you can see it here now, there's your 20. So if I were to type in an equation, I'll call it, see if I can put a vertical line in, x equals 20. See, there you go. There's another little trick. is to get your vertical equation in along the x value you're really interested in. You can see it intersects the curve here. So after 20 days, we are going to have nearly 5,360 downloads or music downloads. With the equation, it's something that's easy to do as well. We can simply take a value here. So if we let x be 20, then we can use the calculator. We'll perform order of operations, of course. We'll evaluate 1.05 to the 21st, multiply that through by 2020. Let me clear that again. So to the power of 20, that equals, that evaluates the power, and multiply by 2020, and there you have it, 5,360 roughly. Okay, and that's it, and that is a way to successfully manage these types of questions.